time for our fifth podcast over chapter 21, right? Our electrochemistry chapter. And so we have finally gotten to the point where we can use our standard potential tables in order to calculate standard voltages. Just need to remember that in those standard potential tables, they're always shown as reduction potentials. And when we have our standard voltages, we have to calculate those by taking the voltage. The standard voltage is equal to the reduction half cell plus the oxidation half cell. So one of them is going to be oxidation. Remember, when we find the oxidation, we have to take the value in our reduction potential and change the sign of it, not the amount, but just the sign. So we got to keep that in mind as we calculate these things. But let's run through our rules for calculating them, and then we'll do a sample problem on how this is going to work. In order for us to calculate our standard voltages, we're finally there after several podcasts so far. Right, remember, we're going to use that equation that we saw earlier, where our standard voltage is equal to our voltage for the reduction half cell plus plus the voltage for the oxidation half cell at standard values. So in order to calculate these things, we need to look up the reduction potentials for both half cells. Again, they're both going to be written as reduction potentials. However, right, one of them is actually going to be the oxidation. So when you look it up in your table, right, your half reaction for the oxidation is going to be written reverse of how it's going to be written in your overall reaction. So keep that in mind. When you're looking it up, you're going to have to look for it written reverse of what you're expecting to find in that table. All right. When you do find that oxidation half step, remember, whatever the value that's in there, you're going to use that value, but you're going to change the sign. So if it's a positive value, you're going to make it negative. If it's a negative value, you're going to make it positive, right? And then you're going to plug that into our equation. And our standard voltage is equal to the reduction plus the oxidation. So you're going to add those two numbers together, whatever you get. All right. Now, if you have a voltaic cell, your value should always be positive. All right. So this seems like kind of like a one-off statement here, but it's actually relatively important and can be useful. Right, sometimes I'll put together a problem, and I think that one of the problems that you're going to be quizzed on, probably in this chapter, is like, okay, if you have these two reactions and you put them together, right, it's a voltaic cell. How do I know that you have added them together to get the right voltage? So you might look up your reduction potentials for two half cells, and you might have, right, for one of them, E naught reduction is equal to, sorry, I'm in the way, oops, is equal to, say, negative 1.00. And for the other one, E naught reduction is equal to negative 1.50. All right, and it might ask, all right, we're going to call this one number 1 and this one number 2. Okay, which is oxidation for a voltaic cell? Again, I'm writing and it looks terrible. All right, so which one of these is actually the oxidation step if it's a voltaic cell? Well, remember, right, we have to use our equation here. Right, the reduction plus the oxidation for a voltaic cell has got to be positive. And I have to switch the sign of one of these two things. If I switch the sign of the top one, plus 1 minus 1.50 is equal to minus 0.50. Well, that can't be voltaic because it ends up with something negative. So what if I switch the sign of the second one, 1.00 minus 1.0, and I switch the sign of the bottom one, plus 1.50, we get plus 0.50. All right, that one makes sense, that one is the one that we can switch the sign of. So it doesn't look like it's a super important bullet point, but it is. It comes in useful, and I swear it's going to come in on our exam that is coming up soon. So make sure you remember that, right? Our voltage is always positive for a voltaic cell. Another thing that tells us, without us even thinking about it, remember, voltaic cells are always spontaneous reactions. So spontaneous reactions, by definition, also must always have a positive standard voltage. That's a good way. So we know spontaneous reactions have to have a negative delta G. They also have to have a positive E naught. All right, last bullet point says never multiply our voltage by any coefficient. So even if your reaction doesn't look like the one that is in your table, right? Even if it looks like, okay, in the table, it has, right, our zinc, is gonna, our zinc 2 plus 2 electrons going to zinc solid, and it gives a reduction potential of, say, 0.768 or something along those lines. It was close to that. All right, well, and this would be negative because it's a reduction. All right, negative 0.768 volts. If you had two, in your equation, 2 zinc 2s plus 4 electrons producing 2 solid zincs, the E naught reduction for that is also negative 0.768 volts. Yeah, that equation is twice as many as the top equation, but we do not multiply voltages by any coefficients. We don't multiply through by anything. Whatever's in that table, we're going to use that value. So keep it the same. All right, that's what our last bullet point is telling us there. So let's do some sample problems working through calculating our standard voltage. Working on sample problem 21-4, it asks us to calculate the standard voltage for the following voltaic cells. All right, so that means that they are going to have a positive overall voltage, so we can double check our math at the end. And so A has lead, solid lead, reacting with 2 silver cations going to form lead 2 and 2 silvers. So I can look up both of these in a standard reduction potential table. Right? And what I'm going to find in that standard reduction potential table is I'm going to find this. I'm going to find lead 2 aqueous plus 2 electrons are producing solid lead, and we're going to have a E naught reduction of negative 0.127 volts. And I'm going to look up and I'm going to find the silver, and when I look that up, I'm going to get that I get silver cations plus an electron are producing solid silver, and the E naught reduction for that is equal to positive 0.799 volts. All right, well, we can tell that the top equation, I have lead 2 is becoming lead. But in the problem, I have lead becoming lead 2. So this isn't the oxidation. This has to be, or sorry, this isn't the reduction. This has to be the oxidation. So I'm going to say that the oxidation for this is going to be positive 0.127 volts. All right, now also, if we look at our silver, we have our silver cation, and it is becoming solid silver. In our problem, I have 2 silver cations, becoming 2 solid silvers, like so. All right, so we are going from something that's a cation to a solid, so this is a reduction. Right? Now, what we found in our table has coefficients of 1. What we find in our actual problem, right, our overall equation, is that we have coefficients of 2. But remember, we never multiply our voltages by any value. So I'm going to leave it the same. It's still positive 0.799 volts. All right, so we can now plug those values in down here at the bottom. So I've got those 2 equations. And notice that I've written out that my silver is actually 2 silvers plus, I'm multiplying that coefficient out in front by everything, so that's 2 silvers plus 2 electrons are forming 2 solid silvers, right? Because we need the electrons to cancel each other out. If there were 2 electrons there, they would cancel out with those 2 electrons. And we would be given our overall equation, which is solid lead plus 2 silver cations are producing lead 2 cations plus solid silver, or 2 solid silvers. That is our overall equation from part A. And so if I want the overall standard voltage for this, right, I'm going to add the reduction and the oxidations together. So I'm going to add these 2 values together. And when I do so, my overall E naught, right, the voltage for this is 0.926 volts. Right, that's all we have to do. All right, I'm going to let you guys look at part B on the next slide, but I'm going to work part C. So let's look at this one here, right, before we get over there, because right, if we notice, part B is just a little bit more in depth and a little bit more complicated than A was, but it's still just going from 2 different half reactions and figuring out, okay, I can look at the potentials in our standard potential tables and figure out which one's the reduction, which one's the oxidation by the way that they're written. C, however, has cadmium to cadmium 2 and zinc 2. And that one's going to have us do one more little step in it. So let's see what we're going to do on part C on our next slide. Well, a lot of part C is actually worked out in advance here a little bit for us, but I want us to work together to see where we got to this point. So when we've got our zinc and zinc 2, right, like this, what we can find in our reduction potential tables is we're going to have our zinc plus 2 electrons are going to produce solid zinc, and you're going to be given E naught reduction is equal to negative, let's go with 0.762 volts. And then you're going to also look up, right, cadmium 2. Right, what you're going to be doing is you're looking for cadmium to be on one side of the reaction and cadmium 2 to be on the other side of the reaction. The only place that you're going to find that in your tables is you're going to see cadmium 2 plus 2 electrons producing solid cadmium, right? Because there are always reduction potentials in our tables. So the reduction for that is going to be negative 0.402 volts. In order for us to figure out which one is the oxidation, right, remember we have to switch the sign of one of these 2. Right, one of these 2 things has to have the sign switched. Right, we're going to switch the sign of one of them. And when we switch the sign of one of them, they must then sum to a positive number, right? Because these are voltaic cells. Our standard voltage has to be positive. So the only one of them that I can switch the sign of, if I switch the sign of 0.402, well, negative 0.762 plus 0.402 is going to give me a negative value, right? We must change the sign of the top one, right? Which then means that we're going to reverse that reaction so that it's the oxidation step, which means that we have now reversed the sign to be positive 0.762. So the overall reaction is now going to be zinc plus cadmium 2, and our electrons cancel. Shouldn't be any electrons once we're done, because if you are going to give off electrons, somebody has to be there to take those same number of electrons. We're producing zinc 2 plus solid cadmium, and so our standard voltage for this is going to be positive 0.762 minus 0.402, which is 0.360 volts. So hopefully we can follow along with what we're getting there with how to calculate our standard voltages throughout these problems. All right, we've hinted at it a little bit in the fact that, right, our Gibbs free energy, we know how to tell whether a reaction is spontaneous or not. And now with our standard voltage, right, if it's positive, we have a spontaneous reaction. Well, if our Gibbs free energy has to be negative for a spontaneous reaction, and our voltage has to be positive for a reaction to be spontaneous, there has to be some sort of a relationship between those two values. And that's what we're going to dive into in our next podcast.